Okay, and we're going. So here's new topic for today, arguably kind of a continuation of an old topic. And I'm going to just leave that as foreshadowing for the moment, and I'll give the reference in a few minutes. So we're going to talk about new coordinate systems, new alternatives to what we call rectangular coordinates, which is the way that y'all have always thought of to represent a location. Is you give the x and y coordinates. That's just what the point is we're so accustomed to it we don't even think about it as being an arbitrary choice, right? Here a couple of nice things. Just a moment of appreciation for rectangular coordinates before we bail on it. And that is, rectangular coordinates are unique. If you give me a point, by which I mean a geometric point, right? Thought of as a geometric object. That point, I can describe where that point is by way of a pair of numbers, x and y, which form an ordered pair, x comma y, and these coordinates are unique. So in the sense that there's only one way to do this. There's only one ordered pair, x comma y, that describes that location. Okay, sadly, this is not the case for the new coordinate systems we're going to talk about. So we need to appreciate this while we have it and then get ready to abandon this convenience of coordinates being unique, because in polar and cylindrical and spherical, they're not. Okay. All right, next. They're what I'm going to call algebraically convenient. If you have if you have a point, for example, and you want to figure out how to write that in terms of standard basis vectors. Oh, well, this is wonderfully nice that the x coordinate is also the coefficient of E1, and the y coordinate is also the coefficient of E2. Well, isn't that handy, right? It's not just to be taken for granted that this is going to always work in any coordinate system, and it's not going to in our new ones. Likewise, analogously and arguably equivalently, if you take a linear combination of vectors in rectangular coordinates, the same linear combination is how you compute the coordinates of the new point. So again, wow, isn't that handy? Very nice, but again, this is a peculiarity of rectangular coordinates, and our other coordinate systems that we're about to see will not have that. So sadly, this is what we have to let go of, and with that said, that disappointment established, let's start talking about polar coordinates. There are different ways to think about polar coordinates. My preferred way is to think of polar coordinates in relation to a particular function, and the function is the conversion formulas. So given the polar coordinates, this function returns the corresponding rectangular coordinates. Now, in particular, how does that work? Well, the idea is that this coordinate here, theta, represents an angle specifically as measured going counterclockwise, arbitrary choice, I grant, right? But that's the convention, counterclockwise from the positive part of the x-axis. And then r is to be thought of as, loosely speaking, and you notice I put this in quotes, it's how far you go in that direction to get to the point that you want to talk about. And I have to put the how far in quotes because how far suggests a distance. Distances are intrinsically positive. And in fact, in polar coordinates, there's absolutely no reason that the r coordinate should have to be positive. At least at this stage, we have no motivation to require r to be positive. So if r is negative, like if your r was over here instead, so in other words, if we're not talking about that point, but if we're talking about a point over here where r is negative, then you just go the opposite direction, right? Kind of stands to reason. Seems plausible anyway. Okay. So again, yeah, this word how far it's not sort of particularly compatible with the idea of a negative value, and thus it's an awkward choice of words. But I don't frankly know any better choice of words for that particular spot there. So, oh well. All right. So pausing real quick. Questions before I go on. Everybody all right? Here's an easy little bit of geometry / trig. We can talk about this right triangle right here. And a little bit of trig on that right triangle tells us that x is our cosine theta and y is our sine theta. Right? Yeah, question.
So if we were to plot the same point on both graphs, it would be the same.
Yeah. So the idea is that if I were to describe this point right here, I would say that its rectangular coordinates are x and y, and its polar coordinates are r and theta. Yeah. So same point. Yes. Does that make sense? Mm-hmm. Yeah. It's just kind of two different ways of describing that location. Yeah. Okay. So we have a coordinate system. We have conversion formulas, and we've got a system. We've got a way of describing where points are. Now, let's see this first disappointment, right? The lack of uniqueness. I claim rectangular coordinates are not unique. Polar coordinates are not unique. So let's talk about this point right here. Well, that point could be thought of as, well, this being the angle. Fine. That value of theta, whatever that is. And that value of theta, maybe I have to go this far from the origin. Let's say that distance is 5 arbitrarily. Then the r coordinate there is 5. And this point in the r theta plane represents that point in the xy plane. Or said differently, r and theta here are the polar coordinates of this point. But a couple of nasty observations. That value of theta, what would happen if I added 2 pi to that value of theta? Now, this is what that looks like in the r theta plane, right? But forget about the r theta plane. What does that look like in the xy plane if I add 2 pi to the angle? Well, 2 pi just means go a full turn. And if you do a full turn, you're still pointing in the same direction. So we still get the same point, right? So this totally different polar coordinate still gives the exact same point in rectangular coordinates. So this is what we mean by a lack of uniqueness. This is one version of the lack of uniqueness. Is everybody on board with that? And it's just because there's only, you can go as far as you want in the x direction and never come back to where you were, but you can only turn around so far until you've turned all the way around and now you're pointing in the same direction again. Okay, here's another issue with uniqueness problem, and that is, what if we do not a full turn? What if we do a half turn? Well, a half turn would have us pointing this other direction. It would have us pointing, let's see here, I guess I'll do it like that. It would have us pointing that way. Well, pointing that way, if I were to, let's see here, in fact, let me do it like this. If I were to go, 5 in that direction, well, that would have me over here, which is not the correct point. But notice how, as in my new angle, my new direction, theta plus pi, I'm going not just the wrong direction, I'm going exactly the wrong direction. Right? Which means that if I just went opposite, if I went exactly backwards, if I did a negative value of r, then I would be going exactly backwards from the direction that I'm pointing, and sure enough, I get to the same point. Right? So this is another way to sort of failure of uniqueness of polar coordinates. It's not just arbitrary numbers of full turns that, of course, don't matter. You can do half turns and just make r the negative of what it had been. Okay. All right. There's another couple of little awkwardnesses that just have to get pointed out. When you're talking about points in a coordinate system, or in particular when there's multiple coordinate systems running around at the same time, like maybe sometimes in what you're doing, sometimes there's polar coordinates, sometimes there's rectangular coordinates, and that's kind of the norm, by the way. If polar coordinates show up at all, it's usually in addition to rectangular coordinates. This notation right here starts to be ambiguous, right? Just because I put some numbers in parentheses, well, that just means these are two coordinates. It doesn't mean particularly which coordinate system's coordinates these are, right? So maybe this is a reference to, x being 2 and y being pi over 6. Maybe, I suppose, it could be that we're talking about that point right there, but it need not be, because this pi over 6 could be the theta, and the green 2 could be the r, which means maybe we're talking about that point. And these 2 points are not the same locations. So which one does 2 comma pi over 6 mean? And I claim it is ambiguous, right? Depending on the context or the circumstance, maybe the person who wrote that might have meant either one of these. So, there's different ways to address this problem. I think an easy one, hard to argue with, is just do this. Right here, just specify r comma theta equals 2 comma pi over 6. Ambiguity gone. And now it's perfectly clear we're talking about polar coordinates. So heads up on that. Do try to be careful. Make sure to remember that your reader is a word reader, not a mind reader, right? And so you have to write down what you mean. Okay. All right. Now here's a nasty little point of confusion. And a lot of students who've learned polar coordinates back in high school step on this landmine, because high schools very often, no exceptions granted, but very often they sweep ugly, confusing points under the rug because they don't want to deal with it, right? So I like to point out that while this equation here is true, this equation here is not necessarily. And it's tempting. So come on, we're right there. Why wouldn't we just go ahead and solve for r? Come on. And the reason why is that in this equation here, r could be positive or negative. There's nothing about this equation that insists that r be positive. But in this equation here, r, it says so right here, is, and then this symbol right there, which means the positive square root. Right? So this equation, this tempting, sort of like, you want to run it into the end zone, solve for r, right? But no, it's importantly, subtly but importantly, not true. Yeah. Oh, I'm sorry. Yeah. So I'm in the chapter 1 notes for Math219, and it's page 25. I think we started on page 24. Yeah. Okay. So, likewise over here, it's tempting to say theta equals arctan. Arctan has a very specific range of values, right? And theta is not constrained in any way like that, right? So again, resist the temptation to solve for theta. And then just be aware of the following example. The moral of the following example is, you have to draw a picture and you have to think about the geometry. The algebra alone, I mean, I'm not saying it can't be done, but the way most students do it, you just can't count on it. You can't rely on it to work correctly. So here we go. Let's think about this following point right here. -1 comma -1. There's nothing weird about that point. Unremarkable, right? I didn't have to search deep to find an obscure, random, weird example here. It's just a perfectly reasonable point. Now, I can take these numbers and I can plug into these equations, and what I see I do know what r squared has to be, and I do know what tan theta has to be. No problem. That's true. Here's another thing I can do. I can enumerate the possible values of r that come out of that equation, right? And I can enumerate the possible values of theta that come out of this equation. And now, real quick recognition before I don't want to get distracted by it, but this 2 pi n, that's just a recognition that when you're talking about an angle, yeah, of course you can always do a full turn, and nothing happens when you do a full turn. Nothing happens when you do any number of full turns. So plus 2 pi n is just kind of this recognition that turning around a full turn doesn't really do anything. Okay, so aside from that, the point is that theta can be either pi over 4 or 5 pi over 4, and that is what this is telling us. Okay, so here's what a lot of students do wrong, though. A lot of students say, all right, well, yeah, look, square root of 2 is really the value, and this is the obscure weirdo sort of like, no, I mean, that's just we have to put it in there because of arithmetic or something, but it's not really what we're interested in. That's just a weird algebraic, coincidence or something, right? And likewise, everyone thinks, come on, pi over 4. That's the one that we're really interested in, and this is just trigonometry is weird, right? But not so. Very importantly, not so. If you take the most convenient value of r, the most convenient value of theta, well, that puts you over here, which is not the point we're interested in. Again, don't blame me, I didn't do it, right? So I just want you all to be aware of this landmine. This is a nasty little thing, and if you don't incorporate a picture and think about what happens in your picture when you make your algebraic choices, you can end up getting wrong answers this way. Is everybody on board? Okay. Nobody showed me this in high school. I was not aware of this issue in high school. Okay. All right. So the actual way to do this is, again, you look at the picture and you think, all right, well, if I were to choose the angle pi over 4, that would have me going this way. How far do I have to go in that orange direction to get to that purple point? Well, apparently I have to go backwards because of where the point is, and it's opposite of the direction of the arrow. Is that cool? Or likewise, analogously, if you use the angle 5 pi over 4, fine, that's that way. How far do you go in that direction? Well, you go positive square root of 2 in that direction. Okay. All right. So heads up, watch out for that landmine. How do we understand equations in polar coordinates? Sometimes you get lucky, and it's either obvious or really convenient. So, for example, here's an equation in polar coordinates, right, in the sense that every variable in the equation is a polar variable, right? And look, that says distance from the origin is 3, so that's an easy one, right? That's a circle of radius 3. Well, of course it is. Now, just to put an algebraic stamp on it, notice if r is equal to 3, then r squared is equal to 9, and of course r squared is x squared plus y squared. That's a basic formula of polar coordinates. That's just the Pythagorean equation on the triangle. And once you make that substitution, then you get the familiar rectangular equation for that circle. So there's an algebraic way to think about this, and there's a sort of a geometric, intuitive way to think about it. Same answer either way. Likewise, theta equals pi over 3 points that way. There being no indication of what r is, r could be any value. That gives me this sort of ray coming out of the origin. Oh, wait, but r could also be negative, and so actually this is the equation of a line. Fine. No problem. You can think of that again geometrically, or you can take the tangent of both sides. Slick move. Recall that we have this identity, tan theta is y over x, and we recover y equals mx, basically. Equation for, of course, the same line. Okay. Sometimes it doesn't work out so nice. Sadly. Frustrating, but true. So, for example, let's look at this equation right here. R equals sine of 2 theta. Tricky little thing. We have to break this down into pieces. I'm going to break this down into chunks of angles. Let's start by thinking about theta as it goes from 0 to pi over 2. There's theta, by the way. It's going to go from 0 to pi over 2. What is theta on the picture? On the picture, there's theta between 0 and pi over 2. This, by the way, notice case 1 that we're talking about. And what happens when theta goes from 0 to pi over 2? Well, the argument for the sine function goes from 0 to pi. Don't forget about that too, right? Theta, it's tempting to think of that theta is always the thing that goes into the trig function. Not in this case. 2 theta is what goes into the trig function. So the argument of sine goes from 0 to pi, and as the argument of sine goes from 0 to pi, the value of that function, in other words, the value of r, sine itself, as its argument goes from 0 to pi, does this move, where it goes from 0 all the way up to 1 and back down to 0. So this is a guide for how I can actually plot what the curve is doing. As theta, as theta goes across these angles, in other words, as my direction does like that, the values of r, in other words, how far do I go in those directions, starts at 0, then it starts to increase, and then at pi over 4 it reaches its maximum, and then it starts to decrease until it comes back down to 0. And you'll notice then that traces out, let's see here, I guess I'll do this in orange, this, what you might call one arch of the sine function, makes what you might call one petal of this little 4-leaf clover that we're about to trace out. Everybody on board? Yeah. So this is basically manual plotting, right, of points. But notice in polar coordinates, in the sense that the inputs are thought of as angles and the outputs are thought of as, and again, air quotes, distances. Is that cool? Now, where it gets weird is when we start thinking about the second case of this. The second case is, let's think about our angle, theta, going from pi over 2 to pi. Keeping in mind that that's the theta. That's not the argument of sine. The argument of sine goes from pi to 2 pi. And as the argument of sine goes from pi to 2 pi, well, sine, aka r, goes from 0 down to -1 and then back up to 0. Now this is, like I say, a little bit weird. I have to now imagine as I point in all of these directions, right? How do I represent on the picture that I'm going negative? Again, air quotes, distances in that direction. Well, I'm going to be going backwards from the directions of these green arrows, and that has me doing basically like this. Again, geometric appeal. And so this curve, if you will, there in polar coordinates on the XY plane is doing like that. It's geometrically challenging, right? Is everybody on board? Okay, I think it is a healthy exercise to keep going. Think about case 3, case 4, right? What's happening over for these angles? What's happening for those angles? And think it through. And what happens, by the way, is that it does like this, and then like this, and then back to where it came from, and it traces out a little 4-leaf clover. That's kind of fun. Is everybody good? All right. Okay, so fill in those blanks. Again, healthy exercise, good little mathematical weightlifting there. Fill in what happens there and there. Okay, Okay, now here's one where the algebra works out again. So back to sort of good news. It's just that there's a little bit more effort that goes into this one. This is not one that I would expect you to have thought of on your own, but it is one that once I show you the trick, I do expect you to be able to recall what the trick was in this case and in analogous kind of scenarios. There's various versions of this. So here's the move. If you have R equals cosine theta, multiply both sides by R. It's a very clever little trick. I did not think of this on my own, but having done this, R squared, well, that's clearly X squared plus Y squared. R cosine theta, well, that is exactly X. And so our equation turns into rectangular coordinates pretty much immediately. And then I can do completing the square. Make sure you remember how that works. Here again, it rears we saw it rear its head a few weeks ago. I forget exactly when, not that long ago. And here it is again. It just comes up from time to time. So it's a good thing to make sure you know how to do. But you complete the square, you can recognize this as being the equation of a circle whose center is at 1/2 on the x-axis, and whose radius is 1/2. Is that cool? All right. Okay. You can go the other direction. Instead of starting with polar and converting to rectangular, what if you have something in rectangular coordinates and you want to convert it to polar? Here's the good news. This is actually arguably a little easier even, because in some sense all you got to do is plug in x equals r cosine theta, y equals r sine theta, and just, then do algebra. So kind of easier. Now in this case I am going to pull a little fast one. What did I just do? I'm sorry, I was looking at the wrong one. I'm going to rewrite the y minus 1 quantity squared. Go ahead and expand that out. And if you do that first, what's nice is that then x squared plus y squared makes an appearance. We already know that's r squared. That saves us the trouble of having to effectively write out a little bit of trig that will then simplify into effectively what we just did here in one step. So that's a nice move. Again, you don't have to do this, but it is convenient. And then also don't forget that, of course, y is r sine theta. And so basically just plugging in your standard formulas and then solve for r, and you get r equals 2 sine theta. So nice, convenient conversion from rectangular coordinates to polar coordinates. These last two examples, by the way, are particularly important and come up regularly. R equals cosine theta is always going to give you a circle kind of centered on the y-axis. And then R equals sine theta is going to give you a circle centered on the... What did I just say? Let me try that again. I think I may have said it backwards. R equals cosine theta gives you a circle centered on the x-axis. R equals sine theta gives you a circle centered on the y-axis. And of course, this constant here, just kind of as an indicator, that controls where the, I guess you could say that controls where the most extreme point is. Another way to say it is that affects where the center is. Okay. All right, this kind of thing comes up a lot. Okay, that's polar coordinates. Let's talk about cylindrical coordinates. Good news. It's pretty much polar coordinates. A lot of people call it polar coordinates in R3, and I think that's very reasonable. Because after all, if you look at the cylindrical coordinates, and here they are, notice that the first two cylindrical coordinates are literally polar coordinates. In the XY plane, it's the polar coordinates of the projection of the point you're interested in. So, the point we're interested in is up here, but it's got a projection down here in the XY plane, and we're literally just writing down the polar coordinates of that projection. So, very handy. The remaining coordinate is just the z that we already had. It's literally the same z. It's how high is that point, you might say. And so everything in cylindrical coordinates is actually familiar. We've seen it all before. We're just combining it in a weird way. Is that cool? Everybody's happy? Okay. So all of our formulas from previously still work. Gotta love it. Couple of easy examples. If I were to set r equal to a constant, think about all the different values of theta, all the different values of z, but r being fixed as a constant, that is going to trace out for us a cylinder. Well, that's a poorly drawn cylinder. Let me try that again. I'll just do it like this. It's going to make a cylinder kind of like that. Bad art. My apologies. Does everybody see that though? Okay. So thus the name, right? So cylindrical coordinates because a level set of the r coordinate is a cylinder. Alrighty. Also, fairly convenient to write down the equation of a sphere. Now, of course, the rectangular equation of a sphere is old news, and then I'm just going to combine that with this fact that x squared plus y squared is r squared, and we get the cylindrical equation of a sphere. Also pretty decent. Yeah? Okay, now here's one that's tricky. Z equals KR. What's going on here? I'm going to tell you what I think is the most convenient way to understand what's going on in this equation. First thing I notice about this equation, of course, it's in cylindrical coordinates, right? Because I see the cylindrical coordinate r and the cylindrical coordinate z, so this is a cylindrical equation. But the next thing I notice, theta is not there. Theta is missing. No thetas. And what that means then is this shape, whatever it is, whatever theta is, doesn't matter. All these different values of theta, all these different half-plane cross-sections, you might say, they're all going to have the exact same equation within those cross-sections. Z equals KR. And Z equals KR is really easy to write down. So I can say, well, here's one of these half planes, just drawn separately, where Z is a function of R, and I can draw this pretty effortlessly in those half planes, right? And I get a line, and now if I've got a line in all of these different half planes, which you might imagine kind of are rotations of each other around the z-axis. All the cross sections look exactly like this. The result then is that this surface is just a rotation of one of those lines. And when you rotate that line, you get a cone. Okay. Now, the tricky part, well, that is one of the tricky parts, right? Missing theta means rotationally symmetric around the z-axis. Nice fact, right? That's a good little tool for your toolbox. Right? But here's another point. I said half planes because I was naively thinking of theta as defining these half planes, but again, that's not really right. I can just as well talk about the other side of these planes. There's nothing wrong with r being negative. It might not be our favorite way to think about polar coordinates, but it's perfectly allowed. And so likewise, it's not just a half of a line, it's a whole line. And so I don't just get this thing rotating around. That rotates around too. And so I actually get then not just the upper part of the cone, I get the full cone. Like so. Just where r is negative. Everybody all right? Okie dokie. Oops. Alrighty, moving along. One real quick thing. Very often, when you're doing polar coordinates or cylindrical coordinates, there are round things in your story. There might be a circle in your picture. There might be a cylinder. There might be a sphere, whatever, right? There's a temptation when you have round things to make a reference to their radius, and because radius starts with an R, there's a temptation to use R to refer to that radius. Careful though, if you are using R to refer to the fixed constant radius of something, then it cannot also be a variable. Right? That's a nasty little issue. Now imagine if you were in rectangular coordinates and you were talking about a rectangular box. Would you want to describe the width of that box as being X? No. I need X. X is a variable. I need to reserve X to be the variable that could be all different values depending on which point I'm looking at. You wouldn't describe the width as X. You'd describe the width as like A or something, or W, right? And likewise, height, you wouldn't call it Y. You need to reserve that as a variable. So likewise here, please be cautious not to accidentally confuse your variables. And now some options. If you want, instead of R, you could call it R naught. You could call it R star if you wanted to. A nice, more visually satisfying hack is to call it capital R. Right? The variable is lowercase r. So, and of course you can also just call it A, or, some entirely different letter. But be very careful. Don't call it R itself. Okay. Alrighty. Spherical coordinates. Also commonly referred to as polar coordinates in 3 dimensions. I do not think that's a good idea. We're already calling cylindrical coordinates polar coordinates in 3 dimensions. You can't use the same slang to refer to 2 different things. That's a bad plan, right? So spherical coordinates is also very importantly different. It does share one of the variables. It does share the cylindrical variable theta, but beyond that, it's all different. And it's importantly, in weird ways that we're going to see in a few minutes, very different from polar coordinates. So please don't conflate those. Okay, so here we go. How does spherical coordinates work? Whoops, I wanted to be in highlighter mode. The theta coordinate defines an angle, again measured counterclockwise from the positive part of the x-axis. Same theta as we saw in cylindrical coordinates, so that defines what I'm going to call a half plane. Right, and again, technically it could be, r could be negative and it could be on the other side. But I want to think of it as a half plane that theta is primarily referring to. Theta points in a direction, and let's just think about that direction. Okay. The next thing we're going to do, we're going to define another angle. This next angle is called phi. It's measured from the positive part of the z-axis. It indicates an angle that is in the theta half plane and where the positive direction of phi is toward that theta half plane. So it's very important. Positive values of phi go toward. Now, it could be negative. Phi could be negative. Fine. If phi is negative, all that means is backwards away from the theta half plane. Is that all cool? Is everybody happy with that? Okay, so we've got theta, we've got phi, and now notice between the two of those, that defines a direction out of the origin, a three-dimensional direction, right? And it could kind of point anywhere at this point. We've got enough flexibility given these two angles to point kind of any which way we want. And with that direction, then again, I can talk about a distance. This, by the way, very importantly, is not r. R is measured in the XY plane. or you might say r is measured perpendicular to the z-axis. This is not. Another thing it's not, it looks like the lowercase letter p. Very importantly, it's not a p. You can't just choose to draw it as a p. It's a new character, probably in most of y'all's experience. This is a Greek letter rho, and it's another one of these moments where you might, silly though it seems, want to dedicate 45 seconds to kind of practicing how are you going to make this new little letter that I'm going to have to do, and make sure that you develop some muscle memory that you don't want to accidentally draw a P, because that doesn't mean the same thing. Okay, so anyway, rho, and again, it's, how far you go in that direction, and again, air quotes, it's not a distance, it's a coordinate, so how far is an awkward phrasing, but, again, I wish I had a better term there, but, the air quotes, I think, suffices, and, it is a distance if rho is positive, but if rho is negative, you just go backwards. Same direction, just exactly opposite. And again, I think that's plausible, right? It's a reasonable instinct or convention there. Okay, so that's how we define these coordinates. And let's do a little bit of geometry on this picture. Now, you'll notice in this picture, we have a triangle that makes an appearance. Let's see, I'll tell you what, I'm going to do this in yellow. We have a triangle that makes an appearance here. Just for kind of artistic convenience, I'm going to redraw that triangle so that I'm looking straight at it. And it's just a little bit easier to do the trig. I don't know. I find that satisfying. And let's see here. Notice that the base of that triangle, right triangle no less, is R. It's our familiar cylindrical coordinate R. And the trigonometry then of this picture tells us this equation right here, R equals rho sine phi. So make sure you know that one, R equals rho sine phi. Or said differently, make sure you can remind yourself of that one. I'll confess, I've never memorized that formula in my life. I'm not good at memorizing rote. I'm not very good at that. But I am really good at concepts, right? And so I remember the picture here, and it takes me about a quarter of a second to look at this picture and remember, and therefore, R equals rho sine phi. Does that make sense to everybody? Okay. All right. So, that's what that is. Big payoff. Because we know what R is, I can plug that in and then notice that our existing formulas for X and Y, R cosine theta, R sine theta, boom, converted to spherical coordinates. I didn't have to analyze, do some complicated three-dimensional trigonometry to figure out what X and Y are. They're just right there. R cosine theta, R sine theta. Boom. It's really nice. Everybody on board? Okay. And then now the other trigonometric piece of this picture is this vertical coordinate, which of course is z. And that's just the other side of the triangle, so rho cosine phi. And that completes our little trio of conversion formulas, right? And so I think it's kind of a beautiful thing. All of it, the main work, the only things in these conversion formulas that I didn't already know, it all comes right out of the trigonometry of a very simple little triangular picture, which again you can see in 3-space. Okay, so cool. We have a uniqueness problem, just like with polar, just like with cylindrical. I got ahead of myself again. Real quick, not hard to persuade yourself that this is another relationship between the variables, so x, y, and z, and rho. relate like this, a little Pythagorean observation. And so the equation of a sphere turns out really nice. Again, thus the name spherical coordinates. Okay. All right. Okay, so uniqueness problems. With polar coordinates, there were kind of two, I want to put that in air quotes also, kind of two different ways to write points in polar coordinates. And of course there's also infinitely many, because you can always add 2 pi as many times as you want, and it doesn't really do anything. So sweeping that under the rug, there's two different ways to do points in polar coordinates, either where you're pointing right at it and go a positive r, or where you're pointing exactly away from it and you go a negative r. Those are kind of your two options. So there's one angle in polar coordinates and two sort of different ways to be, exactly right or exactly wrong in some sense. Well, there's two angles in spherical coordinates, which means that there's 4 ways to write a point in spherical coordinates. And this is a good mathematical weightlifting, sort of geometric brain bender little exercise. I'm going to leave most of it for y'all to think through on your own, but let me just get you started. So again, let's think about a particular point, easily written in rectangular coordinates. So that's the point I want to talk about. You can look at that picture, drop a perpendicular, think about this triangle and that triangle. It's not hard to persuade yourself of certain values here, namely that this angle here is pi over 3, and that this angle right here is pi over 4. That's just a little bit of trig. Make sure you can do that. Right. That said, how would I write this point in spherical coordinates? Well, theta could be pi over 3. This is the pi over 3 half plane. Now, how could I get to that purple point? Well, I could consider this positive value of phi, which points me in the correct direction. And thus I would have a positive value of rho. Or, this is going to seem weird, but it's perfectly legal, I could use a negative value of phi. Keep in mind a negative value of phi means you're going kind of backwards, right? And you can think through the geometry, again good exercise, but going backwards, you can think about what that angle would have to be. That gets you going exactly the wrong direction, which means a negative value of rho would get you right back to that exact same point. So, details to think through. Now that's all on the assumption that we are using a that we are using this pi over 3 value of theta. Don't forget, 4 pi over 3 is another option. So I can measure the angle like so and go all the way around to that half plane. And now let's talk phi. Well, I could have a negative value of phi. Remember, positive is that way. Positive is always toward the theta direction, toward the theta half plane. So I could use a negative value of phi to get me going the correct direction, and then rho would be positive, right? Or I could go a positive value of phi, thus pointing me in the exact wrong direction, and then have a negative value of rho. So a lot of little details there to think through. Again, I think this is a very healthy exercise, very helpful along, for this exercise is to draw yourself a decent picture. Make sure your straight lines are straight. Make sure your horizontals are horizontal. Your vertical is vertical. Take a little bit of care and concern. Make sure your pictures are big enough that you're not trying to, work it all out on a little postage stamp size picture. That's why would you do that to yourself? Right? Give yourself plenty of space so you can see what's going on. That picture is very helpful. So I want to encourage you all again to think through what all these 4 different ways are for representing this point. Everybody happy? Yeah.
Do we talk about spherical coordinate equivalence in higher dimensional space?
Oh, that's a great question. I'm not actually immediately familiar with how one would do that. I'm sure someone's thought that through, but it's not in common use that I'm aware of for whatever. So it can't be that common. Yeah, right. Good question. Anybody else? Okay. All right. Good little exercise. Here's a fun one. Longitude and latitude. Y'all are probably familiar with these ideas. If not, no big deal. It's just a way we keep track of where we are on the surface of the Earth. And the idea is that there is what we call a meridian. It's called the prime meridian. Historical reasons, it's the great circle from the North Pole to the South Pole that goes through Greenwich, England. Again, just for kind of historical purposes. From there, you can measure an angle called east longitude, which you'll notice if I have the Earth arranged on the XYZ coordinate system as I have it drawn here, that east longitude is exactly just theta. That's kind of nice. So theta is east longitude. Then, now a little bit disappointing, we can talk about from there north latitude. Sadly, that is not what phi is. Phi is this angle, and so phi and north latitude are not the same, but they clearly add up to pi over 2, right? As you go further north, your latitude gets bigger, your phi gets smaller. So that, let's see here, so that phi is not equal to north latitude, but it is closely related to north latitude. Is that cool? So combine that with the fact that your distance from the origin, well, if you got the planet arranged as we have here, distance to the origin is the same as distance to the center of the Earth, which is the radius of the Earth, because the Earth is basically a sphere. I mean, again, not exactly, but close enough. And so rho is also something we can just write down. And so, neat fact, if you know the longitude and latitude of a point on the surface of the Earth, you can immediately write down its spherical coordinates like so. Now, why would we care about that? Here's my favorite example. Let's consider this question, and this is, without spherical coordinates, this is a really, really hard question. If you have a point here, I don't know, Moscow, Oslo, something like that, right? There's a point, and then here's another point, Durham. That looks about, I don't know. Anyway, some other point over there, right? Then how would you figure out the distance? The distance along the surface of the Earth. Now, it doesn't immediately strike you as a hard problem. Distances are supposed to be easy, right? But keep in mind, we're not talking about a straight line distance. We can't tunnel under the surface of the Earth, at least not that far, right? We're also not going to be able to do sort of Pythagorean, like I can't just say, oh, well, I can do that and this, look at the longitude line and the latitude line and make a triangle with the distance that I'm interested in. That's not a triangle. We've got a problem here, right? How to find that distance. So the brilliant idea, and spherical coordinates is a necessary link in this chain, is to recognize that if you know the longitude and latitude, then you know the spherical coordinates, which means you know the rectangular coordinates. And if you know the rectangular coordinates, then it's really easy to compute the dot product. Well, dot product is magnitude times cosine of the angle. That means that I can compute this angle by taking an arc cosine. And once you know that angle, then you can compute the distance with an old geometry formula. Really clever move. Right? Does everybody see how that works? Very tricky. Yep.
And that R is the radius of the sphere?
Yeah, that's right. The radius of the Earth, which is, which to be fair is not constant. I don't know if y'all are aware of this, but I know you know that the Earth is rotating, right? But because of that rotation, there's kind of a centripetal force that kind of pulls it outward, and so the radius of the Earth is actually bigger at the equator than it is at the poles. And it's pretty substantial. It's something like 30 miles. I forget, 20 miles maybe, right? So everybody knows that Everest is one of those Himalayan mountains is the highest point above sea level. But the highest point the point on the surface of the Earth that's farthest from the center of the Earth is somewhere in Ecuador. It's not in the Himalayas. It's because of the oblongness. So anyway, that's a digression, but yeah. All right. Okay. So, and again, you can convert this squared out. Notice that it's real easy once you have x squared plus y squared plus z squared. Boom, that's rho squared. Notice that x, again, it's just a matter of plugging in. That's the formula for x. And then you can just solve, and lo and behold, there's your spherical equation. So these kind of conversions going in that direction is usually pretty much just a matter of doing it. Okay. All right. Okay, so that is what I'm going to tell you all about these coordinate systems. What we're going to do now is we're going to revisit change of variables. Let me go back to my general picture here. Here's a change of variables. And the idea of change of variables was that if you have a function that makes your undesirable domain an image of something more desirable, then you can do a pullback and there's a stretching factor, and but the punchline is you turn an ugly integral into a nice integral, an ugly domain into a nice domain. Right, so that was the big idea. And this is how we're going to really capitalize on our new coordinate systems right here. What we're going to do is we're going to consider what would happen if I use my coordinate system functions as change of variables functions. That makes sense to everybody? I mean, there's a lot of details to follow, right? But coordinate systems can be viewed as functions, right? So, for example, here's how you think of polar coordinates. This is the first thing we wrote down for polar coordinates, is that you can think of as a function where if you give me an r and a theta, right, then I can plug that in into there, and out comes an x and a y. Yeah, whatever. Right? So this function, I'm now going to completely repurpose. Had no idea that this was going to happen when we first wrote this down, but I'm going to choose to say, hey, you know what? I'm going to view this as a change of variables function, even though I have no idea what that'll buy me. Yes? Oh, yeah, thank you. I am now in the Chapter 5 notes, page 26. And thank you for reminding me to announce that. Chapter 5, page 26. Okay, so, you've got a change of variables function. Remember, the very first thing we do when we have a change of variables function is we compute the Jacobian determinant, whose absolute value is our stretching factor, but let's compute that Jacobian determinant first. You're going to take your formulas, you're going to take the appropriate partials, assemble as a matrix, AD minus BC and all that to compute the determinant, and when you do that and simplify blah, 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 it turns out R simplifies really nicely. The stretching factor for this function, the Jacobian determinant for this function is R. Now, that's great news. It simplified nicely. Here's the bad news. That Jacobian determinant, R, is not the stretching factor. The stretching factor is the absolute value of that Jacobian determinant. The absolute value is important. So, absolute value of R is our stretching factor. I don't like absolute values. I think y'all are probably with me on that one. All else being equal, I don't want to have absolute values in my integrand. It's just, I have to deal with cases. It's just annoying, right? So here's where we're going to make a choice for our own benefit. Not that we have to, right? I emphasize, math does not dictate that we must do this. We are going to choose to make our own lives simpler. I hereby promise that I will always choose to use non-negative values of r. I'm never going to go over here while I'm doing polar coordinate integrals, right? No negative values of r. But when you do that, if r is positive, then the absolute value goes away. So that's why this is the motivation for making this choice, that we're only going to look at positive values of r while we're doing polar coordinate integrals, so that algebraically our life will be more convenient. Happy? Okay. So now that does come with the cost of, now we are responsible for remembering when we are doing polar coordinates. You got to remember, you're only allowed to choose positive values of r at this point if you want to use this formula for your stretching factor. That's the deal. Okay. Likewise, cylindrical coordinates, morally identical. I have these conversion formulas. I can think of them as a function. I can say, hey, what if I made that a change of variables function? I can compute the Jacobian determinant. It ends up being r again. Not that surprising, right? We already know that cylindrical coordinates and polar coordinates are very closely connected, so this is not a shocker, right? So again, we get the r. Again, that means that we have an absolute value problem because our stretching factor is the absolute value of that. Again, we're not happy about it. So again, we make a choice. I emphasize again, a choice. This is not dictated. This is a clever way to make our own lives simpler. We're going to choose to only look at positive values of r. Negative values not allowed, because of what I want to be able to get out of it, which is that I want that absolute value to go away. And again, stretching factor is r. Everybody good? Okay. Spherical coordinates. Oh my gosh, same deal. It's probably going to be exactly the same, but it's not. Now, we do, again, have our conversion formulas that we view as a function for which we can compute the Jacobian determinant. It's just that, look, it ended up being pretty different here now. Now it's not r. And another common misunderstanding, a lot of students think that rho is just kind of the spherical version of r. It's really not, right? Rho is importantly different. So the stretching factor here, not rho. It's not even close, right? You just got to do the algebra and see how this plays out. But the stretching factor, the Jacobian determinant is rho squared sine phi. Yeah.
Why is it rho squared? Because r was rho sine phi, right?
Yes, but the stretching factor is just a different calculation. So yeah, the answer to the why is about a page of tedious algebra, which, by the way, I think this is a healthy exercise and everybody should do it once in their lives. I did mine 30 years ago. So y'all, your turn, right? It's not that bad. It's good little mathematical weightlifting. It's a good, it'll make you a slightly better mathematician. So give that a try. But this is how the cookie crumbles. It's just this. So now again, we find ourselves in this situation where our Jacobian determinant, and I'd like to call it a stretching factor, but I can't because the stretching factor is the absolute value. Again, I've got to figure out how I can, smart alecky my way around this problem because I don't want to have to deal with absolute values. Again, the analogy breaks down. Up here, the move was, all you have to do is choose to let r be positive, and everybody wins. A lot of people mistakenly think, again, that, rho is kind of like r, so let's just require rho to be positive. What happens when you require rho to be positive? Answer, nothing. Because it was being squared anyway. So it doesn't matter if rho is positive or negative. That doesn't make a bit of difference. What you have to worry about here has got nothing to do with rho. What you need to worry about is phi. You need to prescribe certain values for phi that will make sine of phi never negative. That's the move. And this is the punchline. And again, flashbacks to high school trig. But I just need to always choose phi between 0 and pi. And in doing so, the absolute values go away and we win. Everybody happy? Okay, now I have good news. These values of phi that we're stuck with, that I have to always choose phi to be between 0 and pi. Good. Those are my favorite values of phi anyway, right? So I call this a trade-off, but really it's a win-win. It's, if I promise to do the most convenient thing anyway, then I also get the most convenient version of the stretching factor. So it's not that it costs us anything. I mean, it is a requirement, but we're required to do what we wanted to do. So, it's a win-win. Okay. All right. So, let's do it. Here is a domain. Let's see here. First quadrant portion of the unit disk. So, there's our domain. Over that domain, I want to compute this integral right here. And now let's just, for quick moment, let's consider how we would do this integral the old-fashioned way. And if you do it the old-fashioned way and you slice and dice, notice that, of course, because of the equation of the circle, as you look for the upper bound, right, the upper bound on y for a given value of x is going to have a square root in it. And if you start carrying this through, it does not work out conveniently. Right? It's an unhappy little integral there. If you do this the old-fashioned way, if you do this in rectangular coordinates. Okay, so instead, let's think about how I can view this as being an image. Right? Remember, that's the deal. If you can view it as being an image, then you can do a pullback through the change of variables function. So how is it that this is an image? Now I claim, and we're going to talk through this, but that this rectangle right here, that rectangle has as its image this quarter disk. Let me walk you through why that's true. Let's think about, for example, this edge right there. That edge is where r is equal to 1, and then theta goes from 0 to pi over 2. Okay, what does that look like in the xy plane? Well, r equals 1, and theta goes from 0 to pi over 2. Well, there's 0, and there's pi over 2. So that's what that edge looks like. Is that cool? All right. Let me just draw that a little bit nicer. There we go. This edge right here, theta, constant, pi over 2. R goes from 0 to 1. This edge right here, theta is 0. R goes from 0 to 1. This edge right here, this is the weird one. This is where r equals 0. Okay, well that's weird, but that's just literally that point. So what this function is doing, right, this polar coordinates change of variables function, it's taking that rectangle and it's kind of squeezing it down on the left-hand side. That whole left-hand side becomes a point, and it kind of makes the rectangle kind of open up on the other side like that. Does that make sense? Everybody okay with that?
Wait, how does squeezing on the left side?
Yeah.
The right side?
It just makes it kind of have to bend like that. I mean, if I were to take a rectangle, I'm going to let my left hand here is representing the green side, right? And now my right hand, I'm going to take these points and let that represent the red side. Now, the idea is that as the right hand's, your left side, as that squeezes down, that just kind of makes it do like this. Is that cool? Yeah. Yeah.
Can you explain how you found the theta axis on the left? Like, how did you find the top?
Oh, how did I get the blue one?
Yeah.
Okay, yep, no problem. So let's see here. This, it says right here, is where theta is pi over 2. Theta equals pi over 2 is that way.
Got it.
Is that cool?
Yeah.
And then R was 0, and then R went up to 1, and so that just makes that. Yeah. Cool. Okay, so we've got a pullback domain. That means that my integral that I'd started with, my integral on this domain that I don't like, this integral pulls back to an integral over here. This integral is on a rectangular domain. I love rectangular domains. Real easy bounds for a rectangular domain. That's fantastic. Don't forget to plug in. Well, plug in just means convert the algebra, right? And so x squared plus y squared is r squared. Manufactured example. I made it up so this would work nicely, right? Of course. Anyway, x squared plus y squared is that. And then don't forget, you gotta remember to insert your stretching factor. This is the part that so many students forget. So many students get wrapped up in thinking about the domain and the pullback and the bounds and the geometry of it all. It just slips their mind to insert that stretching factor. But of course, anytime you're doing a pullback, you have to insert your stretching factor. We've already shown that our stretching factor is R. So don't forget to stick in that extra factor of R. Is that cool? Is everybody good? So easy to forget that. Okay, and now it's all downhill from here. Again, our initially we were looking at a bad algebraic option there, but look how easy this one is. Our integrand is just r cubed. Easy antiderivative. You plug in a couple of values. We're done. Super easy. Using polar coordinates as a change of variables function. Yeah.
If there's a case where you're not just looking at the first quadrant, like for example, if it looks like a hemisphere.
Yeah.
You said not to do it while.
Yeah, you can't use r being negative. Yeah, we'll use different values of theta to get those other points. I've got a bunch of examples of that kind of thing. Yeah. We're going to address that coming up here real quick. Okay, before I do though, I want to take a different point of view on what we did here. The point of view that I had here was I explicitly drew the change of variables function. I explicitly depicted the pullback because that's how we've always thought of change of variables. Well, it turns out there's a nicely convenient way to do it if you're doing polar coordinates, and that is you can see all of what happens in the r theta plane, you can see it in the xy plane. So you don't have to draw it. If everything that you need over here, you can see it over here, then you just don't need to draw that at all. So, for example, let's think about the theta slicing. I mean, up here, when I say that theta goes from 0 to pi over 2, that means I'm looking at constant values of theta, various constant values of theta that go across. That's just the theta slice, right? That's how you do theta slicing. Well, I can see those theta slices over here. There's where theta equals 0. Here's where theta is slightly larger. Here's where theta is slightly larger still, etc. I can just see what those slices look like. So, yeah, sure, there is a pullback, and yes, you're going to theta slice that pullback. But everything that you would conclude from drawing that picture and doing that on that picture, you can see it all over here. This is what the theta slices look like. So, very convenient, as it turns out, to do your theta slicing instead of drawing a whole new picture over there and geometrically toughing your way through finding what the pullback domain is. Just do your theta slicing like this in the XY plane. No new picture required. So here's that same example now. Exact same example we were looking at. Same domain, same integral. And here's the change of variables function. There's the pullback, but notice I've got this crossed out. I'm not going to look at that at all. Don't need to. Because once I decide that I'm going to do this in polar coordinates, I can just ask over here, what's my theta bounds? I know I'm doing it in polar coordinates. I know that my slicing process starts there, where theta equals 0. And my theta slices continue until I get to pi over 2. I don't need to do this. Don't need that at all. Is everybody happy with that? So what this does for us, again, it saves us a bunch of drawing. I can just take the domain as I have it and analyze it in this new way. By the way, then let's do the second part of it. Given a fixed value of theta, let's ask what's the range of values for r. Well, r starts at that point where it's I missed it. Where r is clearly 0, and then r ends at this point, which is on that curve, which again, but given this is a unit disk, so that curve is the unit circle, so r is clearly 1. Everybody happy? Okay, so this is what we mean when we say we're doing an integral in polar coordinates. In polar coordinates means pull back through the polar coordinates change of variables function, but draw your picture only in rectangular coordinates and just slice appropriately. Okay, and I guess we're out of time, so we've got a bunch more examples to follow, and we'll see those on Monday. Y'all have a great weekend. See you later.